Okay, this is Physics 1B. This is hour 2 for August 31st. And we're now talking about fluid flow. So there's kind of two types of fluid flow. There's what's called laminar flow. And this is where all the pieces of the fluid kind of flow in this kind of perfect way, like in a tube, let's say, for example. The idea would be that the particles of the fluid are kind of all traveling in straight lines, kind of parallel to each other. As kind of unrealistic as this is, it's a way we think about fluid flow. It's like all the fluid is kind of flowing in straight lines, and all of these, what we might call flow lines, are kind of parallel to each other. A flow line is effectively like you take a piece of the fluid and you kind of draw a tangent line to the direction of the velocity at which the fluid's flowing. And I have a picture over here of this. So this is something that you can easily experience, you can easily understand by looking at what happens when you burn a match or when you burn incense. Okay, and there's a picture of this right here. So this is a picture that shows both types of flow. Okay, so make it a little bit bigger. If you light a match, the smoke that comes out of the match, now in this case, the fluid is the smoke, okay? The smoke that comes out like near the match head starts out very kind of streamlined. I think these are also called flow lines or streamlines. But then as the fluid, or the smoke, interacts with the air around it, it gets kind of tossed and turned and starts to kind of exhibit this kind of behavior right here. Right? It starts off flowing very straight, and then it flows turbulently. And that's kind of laminar flow down here, turbulent flow up here. The main thing to mention is that this is what we will mostly be talking about. We're mostly going to kind of assume that fluids flow like this. We're going to treat them largely as being incompressible and kind of just examine this type of flow. And the reason why is because trying to understand what's happening up here when the fluid gets tossed and turned like this is, I want to say, a lot more complicated, but I might go as far to say as we don't have, this might be wrong because this isn't a subject that I've studied in great detail. But what I understand is we don't have either the mathematics or a theory to really properly describe turbulent flow in a really accurate way. We can make approximations, and I think largely that's what we end up doing. Yeah, you guys can correct me if I'm wrong. Like in the class range, I mean like in general. I mean like the flow, like turbulent flow within fluids is just one of the hardest problems in all of science. Barron's typing something. Maybe he has some insight on this. Maybe you guys can go do your own research. And maybe I could have done more research before this class, but the thing is that this class, we only talk about this part. And maybe I could go see like what kind of... See, so like, what's a problem we could solve if we understood turbulent flow? We could predict the weather. So how do we predict the weather nowadays? The way that they predict weather nowadays is that they construct forecasts, right? And they say, on the news at nighttime, maybe you guys don't probably watch the news, but maybe you go look up on the internet, like what the weather's going to be like. And they'll tell you over the next 7 days what the weather's going to be like, right? Now, in Los Angeles, that might be really easy to do because it might just be that it's going to be sunny for 7 consecutive days, right? But if you live anywhere else where you get a lot of rain, you get stormy days, you get cloudy days, all that kind of stuff. If you want to predict on a day-to-day basis what the weather's going to be like, your one-day forecast is going to be really good, right? The forecast for the very next day is probably going to be pretty accurate, right? Your forecast for 7 days from now, it's significantly less accurate, okay? So what they have to do to predict like the travel paths of storms, the paths of hurricanes, where tornadoes are going to form, all these things, is they have to take like, they do like an analysis of their data, and then they project it out for 1 day, they project it out for 2 days, et cetera, but it's never the case that their projections are exactly accurate because they're dealing with flow of fluids in the atmosphere and clouds that are subject to turbulence. And turbulent flow, you might even, maybe a way to describe it is it's just like random fluctuations in the air toss and turn what the fluid's doing, which makes, since it can be random, it's very difficult to describe. Does that make any sense, what I'm saying? What do you guys think? You guys have any questions? He says it's crazy. I mean, yeah, so if you think about physics, like, well, the way we describe things in physics, you have to have, like, deterministic principles. If A, then B, you know? Force causes something to move. Or, you know, I've got an object that's traveling off in one direction, and then it's hit by another object, and so it travels back off in the other way, right? Baseball comes one direction, batter hits the baseball flows off in the other direction, right? That is something we can understand. But when you're trying to model infinitesimal molecules, and you might understand how the forces work on an individual molecule, right? But if you want to understand how all these different molecules interact with each other, and then how those smoke molecules are interacting with the air molecules, I mean, you're talking about, I mean, you would need a computer that could simulate every single piece of that motion, right? And then you might find that the way that your system evolves, even if you give it the same initial conditions, you might find that the way the system evolves is still impossible to determine, okay? Or the word that's used in science would be chaotic, right? The what's happening within here, it might not be predictable in the same way as in which Newtonian physics is predictable. You might be able to say something about en masse about what's happening, and that's ultimately what we're going to do in this class. When we're dealing with gases, we're going to talk about macroscopic properties such as pressure and temperature and volume and number of molecules. We're not going to be talking about like measuring every single gas molecule and how fast it's going, because that's an undertaking that we're just not capable of yet. All right, I'm just kind of saying too much about this, but the main point is just to say that, like, we're going to treat fluids as if they flow like this, as if they always kind of flow in this way that the molecules are flowing kind of parallel to each other, or something like this right here. Okay. All right, so that's an introduction to fluid flow. And what we want to do now is we kind of want to talk about what happens. So here I'm describing maybe a pipe and it's got water in it, but maybe the pipe's cross-section remains constant, right? So what we kind of now like to talk about, and I think I've had this still pulled up. Can I reset this? So this is a picture of a fluid flowing in a pipe, okay? And we've got these little dots right here. These represent, we can turn them on or off, I guess, but they'll be there regardless. What does the red button do? Ah, okay. I don't know. Wait. Maybe let me just reset this again. Okay, so we've got these fluids, they're flowing. This would be considered to be like laminar flow, okay? We can increase the rate at which it's flowing. We can see how that's measured too. It's measured in liters per second. So we can like up this. Are they flowing faster? Maybe. What if we go like up to here? That seems faster. We go way down to here. They're slower. Okay. And we can even kind of measure the speed if we want to. Now, because the pipe's cross-section that it's flowing through here is the same, anywhere we measure the speed, it's going to be the same. Okay. So I guess what I would ask you guys, oh, and also the pressure should be the same inside of here as well. Although the pressure is going to increase the lower we go because pressure increases with depth. Right? All right, so let's say that we change our pipe for a second, okay? So let's say I pause this. I'm going to take this out of here for now. What do you think happens to the speed of the fluid if I make the pipe skinnier at this point right here? How is the speed of the fluid going through this piece of the pipe going to compare to the speed of the fluid? Whoops. Well, now you can see what happens. All right, let's just reset. Let's move this one into here. It's going to go faster, right? That's your intuition, Delvino, is that if I... And let's pause it again. if I squeeze this here and maybe also here, if we just make the pipe in general suddenly get skinnier, the fluid should flow faster, right? It'll be faster towards the end. Okay, let's see if that's true. Is it yeah, it immediately tells us, but then we can push play and we can see. Right? The fluid basically, it has to kind of flow faster through here. And it's largely because we're going to treat this fluid as being incompressible. But yeah, the fluid flows faster. The narrower the pipe gets, the faster the fluid flows. Okay. What happens if we make the fluid flow through a wider area? Well, then it slows down, right? This may be something you've seen in a river before. If you've ever been floating on a river in a canoe, so you see the speed is extremely small inside of here. It's very fast over here. The fluid kind of like stretches out to fill up these gaps. In doing so, it slows down, but then it speeds up as it moves through this piece right here, right? It's almost like a traffic jam occurs in this region, right? Where there's all this region where the fluid, it wants to get into this fast portion of the pipe right here, but it kind of has to wait for these bigger molecules to be able to slide through, okay? So, yeah, we want to understand why this happens, okay? And there's other things that we can do with this, like we can add in friction and see what effects that has. But we're not going to worry about that kind of stuff right now. All right, so we want to understand that type of motion. And the way that we do so, and I've got another kind of picture for this one. So here's a picture of a similar type of situation. In this situation, what you've got is there's honey that's been picked up by a spoon, right? And that honey is now dripping off of the spoon. And what happens is that the shape that the honey takes on right as it comes off of the spoon is kind of thicker. And then as the stream actually gets skinnier, the flow rate increases, right? So as the honey falls, the velocity of the honey down here ends up being faster than it is up here. Now, why would the velocity of the honey get faster when it's down here? This is from Physics 1A. Gravity, yeah. So it's moving faster. But because it's moving faster, it has to take up less cross-sectional area, basically, so it gets skinnier and skinnier and skinnier. This happens with water, too, out of the faucet, except for it's probably more pronounced with honey. Okay, so in order to understand this, we're going to look at a picture kind of like this right here. So imagine that I have a tube, right? And I've got these streamlines of flow going through my tube, okay? And my tube has a cross-sectional area A on this side, and it has a different cross-sectional area A2 on this side over here. And what we want to understand is how do I relate the velocity of the fluid at this point, V2, to the velocity of the fluid at this point that we call V1, right? And the answer is kind of all throughout here. The way that we try to understand this in terms of like a derivation, and I don't know if you guys think stuff like this is useful, but it's the way that these things are often taught, and I'll kind of go through it. The idea is we're going to talk about an incompressible fluid, okay? What's an incompressible fluid? Something like water. Water is an incompressible fluid in the sense that it's difficult to compress. It can be compressed if you have water in a closed volume, but it's very difficult to do so. It takes a lot of force. And in normal situations, we can consider it as being incompressible. If it's incompressible, then what that means is that if the fluids gets pushed into a smaller area here, that the volume has to kind of stretch out. So the idea is we're looking at a piece of water as evidenced by this cylinder right here. It's a portion of the water flowing through the tube. And we think what happens as that portion of water slides to here and then to here and then to here and then to here and then here until it eventually gets to this portion here where the pipe has gotten smaller, right? And we simply say that the amount of water that we have on the left side is the same as the amount of water that we have on the right side, and that's what we're going to start with. It doesn't even need to be a D here, but we do so because we think it's like some infinitesimal portion of water, right? And then we say, okay, well, how much, this is V for volume in this case, right? We say, how much water is there in the left-hand portion right here? And we say, well, the volume is equal to A1 times whatever the thickness is here, which is being called ds1. So we say, okay, well, it's A1 multiplied by ds1. The other one we say is area 2 multiplied by the length. It's just a cylinder, so over here you have area 2 multiplied by ds2. And you say, well, if the water's moving with the velocity v1 down here, then if you take that velocity of the water and you multiply by the time interval that it takes to move from this point to this point, for example, then that's going to be equal to the velocity times time, right? So you just say, okay, well then I replace ds1 here with velocity times time. This is funny to me because I've been teaching 1C for years, and when we talk about electrical currents, we do exactly the same thing with this type of diagram right here. On the right-hand side, we say the distance that the water flows over here. It's going farther right now. Can you guys see that? The ds1 and ds2 is bigger. It's bigger because the velocity is faster. So whatever that velocity is, we would then say that we can write down that it's a2 times v1, or sorry, times v2. And then also times dt. And then we simply say that the times are going to be the same, right? It's some infinitesimal time interval that we've put into the situation, but the one thing that's going to be the same between this piece and this piece is the time that it takes to get from point to point. So the time it takes to get from this point to this point should be the same as the time it takes to get through this shorter distance right here. And that's just because it's going slower than it is up here. So the dt's cancel, and we get this equation. This is a really useful equation for fluids. We call this the continuity equation. It says that if you take the area of the tube and you multiply by the velocity, that should be a constant. A times v is a constant. If I take the area of the cross-sectional area of the tube and I multiply by the velocity at which the water's flowing, this gives me what's called the volume flow rate. And the symbol that your book likes to use for this is dv dt. Now this is a volume. The unit would be like either meters cubed per second or liters per second. Okay. The continuity equation. We're going to use this to solve some problems. It's pretty handy. It tells us that this quantity, area times velocity, is constant. And if you look at the units of this, you get meters cubed per second or you get liters per second. And then we use the symbol dv dt. I put some other equations that I wanted to include with this. I mean, I got a lot of notifications. I need to read some of these. There. Oops. Cut. There are a couple other scenarios in which we're going to be using this equation, and I wanted to like put them all together right here. So in addition to volume flow rate, we can also have mass flow rate. Okay, what's mass flow rate? Well, if I take density times volume, I get the mass flow rate. So another thing that we can have, mass flow rate right here, would be density of the fluid multiplied by dv dt. And then volume flow rate I have written here. It's the same thing as we have here. But then there's this one too, and I don't know because it's the first time I'm teaching this, but this is another equation that we can have. If the fluid is compressible, so what's a compressible fluid? Maybe I ask that question, see if you guys know. What's an example of a compressible fluid? Remember, fluids are gases and liquids, right? Oxygen, perfect. Good example. Oxygen is a compressible fluid, right? That means that if I have oxygen in a tank, I can squeeze it. If I blow up a balloon, right, I can take that balloon and I can squeeze the balloon. I can make it occupy a little bit less volume, which then makes its pressure increase, right? Pretty much any gas is going to be compressible because the molecules of the gas are so far apart from each other that it's not difficult to squeeze on that gas. And yeah, so if the fluid is in some way compressible, and that means the density changes from point to point, then this gives you kind of the more general version of the continuity equation. Okay. We'll do some problems here to kind of see what you guys thought was. I want to see what this question is real quick. All right, so yeah, let's do a problem so we can understand how we use this equation right here. I think this is the one we want, right? It's that one, and then we do these later. Okay. Oh no, what did I do? Okay, just need to be careful about. Okay, so it says incompressible oil with a density of 850 kilograms per meter cubed is pumped through a cylindrical pipe at a rate of 9.5 liters per second. The first section of the pipe has a diameter of 8 centimeters. What is the flow speed of the oil? What is the mass flow rate? The second section of the pipe has a diameter of 4 centimeters. What are the flow speed and mass flow rate in that section? All right. So let's draw a picture of this. So we've got two sections of a tube. One is kind of fat and wide. Oh yeah, I need to hold Alt if I'm doing this. We've got two sections of a tube. We got one piece here, and then we've got another piece over here. What is it? 8 to 4, so it's like half the size, right? So the tube basically comes down and it's about half as big. And it's a tube, so we need to kind of like connect the sides of this. Okay, so we've got our tube. We know the radii of these as well. So let's kind of indicate that here. So if this is the center of this, got one radii and another radius. We're going to assume that both the center of this pipe and the center of this pipe are at the same level, because if they change height, there's going to be an effect too. All right. We know that the density of the oil is given by this right here. The oil is kind of flowing through the pipe here. I wonder if I can fill. Can I fill that with a color? I don't know. Maybe with this. I mean, I can make this thicker. So this is all kind of filled with fluid in here. The fluid's flowing. Okay, so it's flowing in a certain direction. So we've got the fluid, and it's kind of flowing like that. It's being compressed, so the rate at which it flows has to increase. It's going to flow with some velocity out this side that I'm going to call V2. It's going to be flowing in this side with some velocity that we call V1. We're given that it's pumped through a cylindrical pipe at a rate of 9.5 liters per second. What's that going to represent? What's 9.5 liters per second represent? Is it V1? What is V? V is velocity. Liters per second is not velocity, right? What is that going to be? It's the flow rate, right? So this would be what we call dV dt, or Just a second ago, we said that's equal to something, right? That's equal to area times volume, right? This is going to be the volume flow rate. It's the thing that's going to be constant, basically, according to the continuity equation. So this is effectively the area of the pipe multiplied by velocity is what that is, basically. All right. So part A. Part A states, here, let's write this real quick here. This is a radius R1 that's equal to 8 cm. And over here, the radius 2 is equal to 4 cm. Part A. If the section has a diameter of 8 centimeters, what is the flow speed of the oil and what is the mass flow rate? Okay. So if the pipe has a diameter of 8 centimeters, can you guys figure this out? What would the velocity be? So this value, right, is equal to the area here, if we call this one A1, and we call the area here A2. This is constant, right? So 9.5 liters per second is equal to A1 V1, but it's also equal to A2 V2. For part A, can you guys solve what is V1 going to be equal to? Oh, you're right. These are not radii. He points out this is actually, that's the diameter. So the radius would be 4. Thank you. This is 4 centimeter radius, and then over here you would get this 2 centimeters. Thank you for pointing that out, Tom. Okay. Wait. What was the question just a second ago? Or what was the answer that you just gave? I think was that Baron. Go ahead. Yeah. Can you guys calculate it? Just do it yourselves? Tell me what you get. Do you have to change the units? I'll let you guys think about it. So try to solve. What's the velocity equal to? So none of you guys answered my first question, which is, do we have to convert the liters or the meters cubed? Yeah, what's the relationship? Do you guys know? How is 1 liter related to 1 meter cubed? That's right. Yep, that's right. So you could use that to figure it out. Someone also said 1 liter is a decimeter cubed. What's a decimeter? 0.1 meters, right? So I think 1 liter is... Is that right? Yeah. what you guys said is true as well. 1 ml is 1 cc, or 1 centimeter cubed. And you could figure it out from here too, because this would be 1,000 liters. Ooh, this is point. This is 1 times 10 to the negative 3 liters. And this would be 1 times 10. So centi is 10 to the negative 2, and you cube it, so you get 1 times 10 to the negative 6 meters cubed. Divide by this, you get the same thing as what we have up here. Okay, so Koa got, someone had answered 1.9 meters per second. Is that right? You guys agree? Any more time? You got that too? Okay. So let's just go through the calculations. So we have basically, we know A1 V1 is equal to 9.5 liters per second, but we can convert that, right? So 9.5 liters per second, which we can convert by saying that 1 liter is equal to 0.001 meters cubed. And then if I want to find V1, I just need to take this whole thing, which is going to become 9.5 times 10 to the negative 3 meters cubed per second. And then we divide, oh man, it looks kind of weird, doesn't it? Meters cubed divided by seconds. We're dividing by the area. Area 1, it's 4 centimeters, right? So we got to divide by pi times 0.04 meters. We got to square that. And you guys are saying you got 1.9 meters per second. Just going to verify with your calculators you get the same thing. And I'm going to do the same. .89 is what I got. So 1.9 sounds good to me. All right, any questions about that? All right, it also wants us to find the mass flow rate. So if we go back up to here, this is really easy because mass flow rate is just density times dV dt, right? So to get the mass flow rate, let me do this another color. Nope, draw, red. So mass flow rate. This is going to be equal to rho times dV dt. Our density is the density of oil, which we wrote down right here, 850. We write that, or multiply it times our, so we've already converted this here. We have meters cubed here, so we're going to need to use the 9.5 times 10 to the negative 3 meters cubed per second, right? Yep. So I'm kind of writing at an angle here, I apologize. So you end up getting rho whatever that's, 850 times 9.5 times the negative 3. So this is going to give us about 8 kilograms a second. So that's the rate at which the mass is flowing through the tube. It feels like when you put it in terms of mass, that seems like a lot of mass. You know, it's like, imagine a dumbbell that's 8 kilograms, kind of every second is flowing through this thing. All right. You guys have any questions? Okay, part B. It says the second section of the pipe has a diameter of 4 centimeters. What are the flow speed and the mass flow rate in that section? Okay, so first of all, is the mass flow rate going to change? If it's just density times dV dt, and dV dt is a constant, the mass flow rate's the same, right? Yeah, it's not going to change. All right. But if I want to find the flow speed, which would mean I want to be finding the velocity 2 right here, right? Then I just need to use this equation now, right? It tells me that basically velocity 2 is equal to a1 v1 divided by a2. Right? And because a2 is smaller than a1, velocity 2 is going to be larger. Right? a1 v1, well, that's just this, right? It's the, we said it's equal to all this stuff, right? So in the numerator we can put 9.5 times 10 to the negative 3. And then, that's a1 v1. And we divide this by a2, which is pi times the radius of the other one is, scroll just a little here. It's 2 centimeters for the radius. So we plug in here 0.02 meters, and then we square that. And we end up getting whatever we get. I'll let you guys calculate that and tell me what you get. So I got 7.6 or so. That sound right to you guys? I could have gotten it wrong. Yeah? Okay. What's the ratio here going to be? How much faster is it? The pipe cut in half by a factor of 2. How much faster does the water go? Factor of 4, exactly, right? Yeah, you guys got it. Because it's squared, right? And we could see that if we did this in a different way. The other way to calculate this would have been V2 equals A1 over A2. Well, A1 over A2 is just pi times 0.04 divided by pi times 0.02. And then we would multiply by V1, which is 1.9 meters per second. But then you look at this, and you realize, oh, it's 4 divided by 2, which is 2, and you square it, so it's quite literally just 4 times 1.9. I like that way better. That, to me, shows a little more about, and you should get the same answer, approximately. Yeah, you get 7.6, so there you go. So something to keep in mind is, do you guys have any questions? This problem is pretty simple. The whole point of this problem is just to get an idea of how we define things. What is mass flow rate? What is volume flow rate? How do we find one velocity given that we have another velocity and that we know the areas of the pipes? All that kind of stuff. But the biggest thing to understand here is for almost all the problems that you guys do, you kind of have this equation in your back pocket, so to speak. All right? If you're given a problem and you don't have enough information, often this is going to be the equation that you're going to use to gain information, if that makes sense. All right, so just keep that in mind as we go along here. We'll be using this and all that, but like, just keep in mind that this is something that you'll always be able to work with, because the vast majority of problems that you'll see, I think like almost all the problems you'll see, this equation is going to be applicable. And the way you know it's applicable is because it has the word incompressible in it. As soon as you see that word, incompressible oil, incompressible water, whatever it is, you get to use this equation. So it's something that's going to give you the power to solve problems, as we will see, as we solve some more difficult things. Okay? Do you guys have any questions? Okay, so what we'll do next is I have 3 problems here that we're going to solve. They're all just variations of different things. They require us to develop one more idea, which, here, where is it? I guess I'm going to have to, I guess I didn't copy it over. I thought I had, but I didn't. It's just not there. Oh, technically we could use this picture here, couldn't we? No, we're not using that picture, though, because I have another picture. Anyway, so for now, I'm going to go ahead and stop the recording, and then we'll take a break, and we'll come back and get to that stuff. This time we'll just take like a 12-minute break. We'll start again at, it's 11-minute break now. We'll start again at 10 after, so 12:10.